Morning. How many of there? Only 5. Are you able to see the screen? Am I audible? Can you? Okay, good. What we discussed yesterday? We discussed about line coding and then block coding, then scrambling. These 3 points mainly we discussed. And the line coding, it is conversion of data element to data signals. And while there are several line coding techniques are there, which we have seen here: unipolar, polar, bipolar, multi-level, multi-transition. These are some of the techniques, and in each of them, again, there are sub varieties are there. Each one has the different characteristics, but while choosing this line coding, we have to ensure that baseline wandering is minimized, DC components are avoided, self-synchronization is possible, built-in error correction is available, immunity to noise and interference to some extent, and less complexity. These are the aspects we keep in view while selecting a line code skill. Okay. Then this we discuss about block coding. Block coding mainly ensures synchronization and error detection. Of course, it enhances number of bits actually. So, but next, what we discuss is scrambling. Scrambling is a technique used for avoiding continuous zeros in the stream. Okay. So, to avoid that, there are 2 techniques are there which we discussed yesterday. Those are, yeah, one is B8 Z8, then another one is HD P3. So here this eliminates occurrence of continuous zeros. That's number 1. 2, it doesn't increase number of bits. It remains same before and after scrambling. Number of bits will remain same. Whereas in block coding, number of bits may increase after coding it. Similarly, even in line coding also, the number of bits may vary between before conversion and after conversion. But in sampling, it doesn't vary. It remains same. So that's different. Okay, then we talked about modes of communication: serial and parallel. So parallel is number of bits sending parallelly at a time, and so that for every clock pulse we will be sending multiple bits simultaneously. But disadvantage is because you have to send, we have to carry 1 bit on each line. We need that many number of wires, so that becomes costly, expensive. Next thing is it becomes more prone to the failures. If that means any of them can fail, reliability is less, and complexity. That means maintenance also becomes little difficult. So that's a major pros and cons of this one. But because many of our process the data in parallel, so it is easy to interface to that. But alternatively, serial communication is available. Serial, again, there are 3 varieties: asynchronous, synchronous, and isochronous communications are possible. But here we will convert these parallel bits into serially and send 1 at a time. For every clock pulse, 1 bit is sent. So you need only, in principle, or strictly speaking, only 1 wire is enough, because we are sending 1 bit at a time. Okay. But because it is 1 bit per clock pulse, it becomes slow compared to parallel communication. And at the same time, it becomes less expensive, less complex, and more reliable, because maintenance of one line in a good condition is good. At the same time, you may say that if that line fails, a typing is fail. Yeah, whether it's one line or multiple lines, the failure is failure. So there's not any such difference. Okay. Now there are three types of serial communication: asynchronous, synchronous, and isochronous. Asynchronous communication, the data is transmitted asynchronously. That means anytime it can start, anytime it can, and after sending a certain number of bits, it is stopped. So that means receiver, because the data is not continuously coming, receiver is not always synchronized. So it should be able to detect start of the data stream, then synchronize itself to that, then receive all the bits at the same rate what is being sent. That means clock rate should be same as sender and receiver, but stopping and stopping, where the bit pattern starts, where it ends, depends on the bits data availability at the sender. So that's why it is called as a asynchronous communication. You can see here one stream of this. Let me, yeah. Let's say this is one stream of bits, and here normally character by, we assume that character by character is represented with 8 bits. Okay, 8 bits there, and it is always preceded by a start bit and succeeded by stop bit. Okay, so that's why total becomes 10 bits for sending a character. So, but these characters may come to the sender at any time. So that's why the gap between one character to next character need not be uniform. It can be any amount of data. Maybe one character comes now, second character may come after few minutes, next minute can come after few hours, like that. So the gap is not uniform here. So that's why the receiver should be able to detect when the stream is starting. So that's why this start pulse is, start bit is required. Start pulse or start bit. Then after that, this many number of bits. Of course, this is fixed. How many bits we are data we are sending it. Similarly, it will be followed by stop bit. That's how receiver can detect all the bits from this received bit. It try to detect errors if there are any. So if there is no error, it passes on to the processor. That's how it is. Because data is coming asynchronously, it is called as asynchronous bit. And always there are 2 extra bits, one stop bit and one start bit. Sorry, start and stop. That's how it is. And compare this with the synchronous transmission. We send bits one after another without start or stop bits or gaps. You can see here. Okay. So assume that this is a stream, this is another stream, this is another stream, this is another stream, like that. Okay. Here we send a stream of bits. That means it is a continuous flow of bits, at a particular data rate. So that we call it. That is always synchronized with clock. Okay, this is synchronized with the clock. This bit transmission is synchronized with the clock, and it's a continuous display. Suppose when there is no data at some point of time from the sender, so it has to send some dummy data to maintain that data stream in the line. Okay, and here, because you are sending in a continuous basis, you don't need that stop and start bits. You don't need that because it is continuously going, and receiver is always synchronized at the same clock rate with the sender. So it will be able to receive and receive. Of course, if there is a mismatch, it doesn't work. There should be perfect synchronization of receive clock at the receiver as well as clock at the sender. And similarly, if you compare with the previous one, here also clock rate should perfectly match both of them. Okay, but only thing is that clock rate is applicable from the start bit to stop bit. Okay, during this time it should synchronize perfectly, synchronize, then you will be able to. That's the thing. Okay. Now, of course, these bits sometimes, as we go into our subject, actually, it is they are divided into different frames. Each frame will be identified with certain numbers and then they'll be sent. Those things we will be understanding in more detail as we go into the next unit of the subject. And third variety is isochronous transmission. When we have multiple types of information we are sending, let's say video we are sending. When you talk about video, it comprises of images, frames, and audio also, right? When both are combined, then only it becomes a real video. So there should be a perfect synchronization between audio frames you are sending it and image frames what you are sending. So if they are not synchronized properly, then there will be a mismatch. You will not be able to appreciate the video. Okay, so that means our lip movement should always match with what the audio coming there, image and audio. So then only it gives a good effect and it will be appreciable. So that synchronization among the different frames of transmission is taken care in isochronous transmission. In case of synchronous transmission, simple synchronous transmission, there is only one type of the data continuously flowing. So you don't need that additional synchronization. Whereas if you take a specific application like video, where you need synchronization between audio and images, then you need further synchronization in addition to frame synchronization, right? So that is taken care in isochronous type of communication. So that's the difference on all these varieties of communication modes: parallel communication, serial communication, and serial communication, asynchronous, synchronous, and isochronous. So those are different things. And before we get into the next topic, let's see some questions whether you understood those things properly or not. 2-3 questions, let's see, and then we can move on to the next topic. Okay. Now tell me this question. Are you able to see this screen? How many? Only 21 today? I think CR, daily you just note down the numbers over present and send it through WhatsApp to me. And at the same time, in case CR is not present, anybody present, please note down the attendance, all the numbers, and send to me. And moreover, from today onwards, we have to enter into the ECAP as well as LMS also. So that's why it is required. Please record by one of you, either CR preferably. If CR is not in the class for any reason, anybody in the class. But the CR please inform to others and ensure that it is noted down and sent. Okay. Now let's see. In a dash transmission, bits are transmitted simultaneously, each across its own wire. Can you answer this question? Out of this, which one? Yeah. Okay. Fine. In dash transmission, bits are transmitted over a single wire, one at a time. What is the answer?
Serial, both A and B, sir.
Okay, good. And in asynchronous transmission, the gap time between bytes is in asynchronous. Yeah. Can I come again? Yeah, again, once again.
B, sir.
Yeah, good.
Variable, sir.
Good. Yeah, good. And just one more, then we can go into that. Okay, dash is the process of converting digital data to a digital signal. Just now,
Analog to digital.
Line coding, sir.
Line coding, yes, correct. Line coding is okay. Block coding, normally what do you do? It is used for synchronization as well as error correction. This, okay. Whereas scrambling is used to avoid long sequence of zeros. So that's the difference. And let's go to the next topic. So that we are going to discuss about multiplexing. Though you are familiar to some extent about multiplexing, but let us review once again. So multiplexing is useful for effective utilization of the bandwidth. Okay, that's the main purpose. Bandwidth utilization is a wise use of available bandwidth to achieve a specific goals. Efficiency can be achieved by multiplexing. That's the main uh, purpose of this one. And privacy and anti-jamming can be achieved by spreading this one. Spreading. This also we will see. And of course, we may have heard about spread spectrum techniques. So the spreading of the spectrum gives two advantages. One is the privacy, and the next is anti-jamming. This also we will see as we go into the class. Okay. But multiplexing, simple multiplexing is efficiency. It improves efficiency of the bandwidth utilization. Okay. Now, as you know, there are varieties of multiplexing techniques: frequency division multiplexing, wavelength division multiplexing, and time division multiplexing. Okay. In this, of course, there are two varieties: synchronous time division multiplexing and statistical time division multiplexing. So this we are going to discuss in more details now. Okay. Dividing a link into channels. So logically we are dividing logically or physically. Some cases, when you come to the frequency, physically also we can divide it. And then each one is shared by different people. So while we are multiplexing incoming data into a single stream and sending it, we demultiplex at the same time. Okay. In between, it is shared by this many number of inputs. Okay. And similarly, it is demultiplied is given that many number of output lines here. So that's what real meaning of multiplexing and demultiplexing. Now, as you see, there are broadly, mainly frequency division multiplexing, wavelength division multiplexing, and time division multiplexing. Apart from this, you may come across code division multiple technique that also is a combination of few of them. That also we will see in this. That comes really actually under spectrum spreading technique. Okay. So what is the frequency division multiplexing? When you have a large range of spectrum, that can be divided into smaller parts. Let's say this entire thing is a spectrum. So that can be divided into smaller parts, and each part can be assigned to a user. So assume there are say 30 megahertz channel is there, and divide into, and the 3 users are there. You can divide into 3 10 megahertz channels, and each one can be allocated to one of them. So each one transmits in his bandwidth what is allotted to him. Maybe you take it as a 0 to 30 megahertz, 0 to 10 megahertz one person, and 11 to 20 megahertz another person, 21 to 30 megahertz another person. That's all. So his data or his information travels only in that band. Then similarly, it is demultiplied and out to the corresponding people. So in this case, because though entire bandwidth available is very large amount, but since it is divided to each of them, each one getting a small amount of data, and amount of data you can transmit through given a bandwidth can be calculated using our earlier formula, channel formula or Nyquist formula, right? So as the bandwidth, it is always proportional to the bandwidth. So when you are dividing the bandwidth, each one is getting only some part of the capacity to transmit the data. I mean, if you compare to 30 megahertz channel, it can transmit 30 Mbps, let's say for example. So 10 megahertz channel can transmit only 10 Mbps. So that means each one is getting a part of it. So they will not be able to achieve that. But what is the advantage? That channel is available continuously for the user. All the time it is available. Okay. So you can continuously keep sending at the rate of 10 megahertz, as per our example. Okay. So that is the difference between total capacity spectrum is divided and each person is allotted a part of it. That distribution can be uniform or need not be uniform. Also, it depends on the administrator. So whatever way he is interested, he can allot it. So, but basically that's how frequency division multiplexing works. But here there is one more disadvantage. When you are dividing the frequency into multiple streams, it is not so simple because our devices, whatever we use at multiplexing and demultiplexing end, they are not so perfect. That means it doesn't work as a perfect filter, that means starting from 0 to and cutting off at 10 megahertz. Similarly, starting at 11 and cutting off at 12 megahertz. So these in a normal practical designs, they'll spread little on both sides. So that's how there'll be a crosstalk. This one. That means neighbors data also can get into or can be accessed or pass through these filters, and of course finally through the channel. That generates crosstalk. To avoid that, we always keep some guard bands between these frequencies. So that way, assuming that one guard band is used between these two, another guard band is here. That guard band may be 1 megahertz, let's say. So that means 2 megahertz, 1 megahertz here, another megahertz here is wasted for guard bands. But that is required to minimize crosstalk. So that is another disadvantage of this one. Some amount of spectrum is wasted here. So those are some aspects of this. But one more disadvantage also there. When there are too many panels are there like this, and if these filters are not perfect here, they can also generate one more called intermodulation products, which can get into other part of the spectrum. That also we have to provide. All these things are some merits and demerits of this. So that's by keeping in view of all these things, we have to utilize this frequency multiplexing and design system appropriately. FDM is analog multiplexing technique that combines analog signals. This is a frequency sequence. Right? Now, example is like this. You can say one part of this thing is there, say spectrum. One user, let's say we are voice, somebody's voice is coming, another voice signal is coming, another person, third one. So here it is modulated on one single one carrier F1. This is carrier modulator and carrier 2. This can be carrier modulator and carrier 3, and all of them can be combined here because there are different carriers. So different carriers. But unless we modulate it, because normally if we take baseband device signal, it occupies 0 to 4 kilohertz, whatever, or 20 kilohertz, whatever we select it. So they all of them will be in the same band. So they cannot be multiplexed and sent. So for multiplexing purpose, we have to modulate over different carriers. So those carriers are spaced apart conveniently as per design, so that we can multiplex and send as a single signal. And similarly at the receiving end, so using that you filter each part of the modulated signal separately and then demodulate it and extract original switch signal and hand over to this, the concept. So this is how it works. Here actually comes the intermodulation products, because so many are mixed here. So that's why we have to take care of intermodulation carriers also. So they should not go beyond certain level. So otherwise they will interfere. They will cause more interference with system. Okay. Example: assume that a Y channel occupies bandwidth of say 4 kilohertz. We need to combine 3 Y channels into a link with a bandwidth of 12 kilohertz. Okay, from 20 to 32 kilohertz. Assume that. Assume there are no guard bands here. So what happens here? We shift modulate each of the 3 Y signals to a different bandwidth. We use 20 to 24 first Y signal, and then 24 to 28 second Y signal, then 28 to 32 third Y signal, so that they can be multiplexed and sent. What is it here? As a problem states, there is no guard band here. You can see 20 to 24 occupy this, 24 to 28, 28 to 32. Okay, they can be multiplexed. Similarly, this thing will be multiplexed and hand over to them. Okay. Right. There is another guard band example is here, and you can see that. So if there are 5 different frequencies we are sending it. Each one is separate a small part. 10 kilohertz here, 10 kilohertz here, 10 kilohertz here, 10 kilohertz. Let's say that. So total bandwidth occupied is what? This is first channel 100 kilohertz. This another, this another, this another, and then totally 500 kilohertz. Plus there are 4 guard bands. Look at this. One here, one between these two, one between these two, one between these two, one between these two. So total bandwidth is 540 kilohertz. So this is how we design system. Okay. Example is given here. Okay. Now let us get into hierarchy of these sizes. How this multiplexing is done, because you can go on multiplexing to a large size of the carrier. Let's say 12 Y channels are multiplexed, which can give each of them is 4 kilohertz. So ultimately output is 48 kilohertz, right? So that is called a group channel. So 48 kilohertz channel, which comprises of 4 Y channels, 4 multiplied by 4 kilohertz. That is known as group channel. 5 such groups are multiplexed, then generates supergroup. Okay. Then 10 such supergroups generate one master group. Okay. Then 6 such master groups generate one jumbo group. Now we can see the jumbo group bandwidth. Okay. Effectively, it is 16.984 megahertz, which can carry 3600 voice channels. Okay. So we can go on again right from the beginning. You can look at that. So 48 kilohertz here group channel, whereas 10 multiplied by 48, so it becomes how many here sorry, 5 such groups, it becomes 240. Then 10 such super groups becomes 240, and then 6 such these things. Yeah, this is 48. 48 becomes 240. 240 becomes 3.52 megahertz. 3.52 becomes 16.984 megahertz. That's how it is. The names you have to remember. Okay. Group channel size. Similarly, super group channel size, master group channel size, jumbo group size, channel group size. These things you have to know, remember that. Then this is really in a original or mobile system when it is invented. It's called as amps. There, how these channels are divided. That's an example given here. And then coming to the next type of multiplexing technique is wavelength division multiplexing. Right? This is similar to frequency division multiplexing, but main difference here is it is optical signals. These are optical signals. That's why we call it a wavelength. So different wavelength signals can be, instead of calling frequencies, we call it here wavelength. They can be multiplexed and sent. But it is, process is same, but only thing is devices we use are different. Okay? Because this optical range of signals, we use the different devices, multiplexing as well as demultiplexing, for doing that job. So WDM is an analog multiplexing technique to combine optical signals. Okay. So we use a multiplexing prism here, another prism here. So deep for demultiplexing. Okay. Right, but it is almost identical to frequency division multiplexing in operation. So again, we are here also we need to give some guard bands and between the wavelength. Similarly, overall intermodulation also we'll have to take care on the thing. But only thing is it is an optical range of frequencies. Okay, and we need to separate different type of cable here to carry optical signals. Now, third variety is, yeah, it may, our session may end in the 10 minutes, but please rejoin again. We take another 5 minutes, then we can close finally. Okay. Now, coming to TDM, time division multiplexing technique. Here we are dividing or sharing the channel in time domain. If you compare in the previous two cases, we shared the medium in frequency domain. That means the channel with bandwidth available is divided in the frequency domain, and each of them is allotted a certain frequency range. It is that means entire frequency range available is shared, divided into. Whereas here we are dividing the time into multiple slots, multiple time parts. Each time slot is allotted to different user, so that all the data can travel through the same line. Here, so let's assume that there are four users are there here. Four users are generating data. All the four users data, this is a single channel. It is not like when entire bandwidth is allotted to each user for the duration given to him. Okay, entire channel is available for the duration given to him. Whereas in a frequency domain system, part of the frequency is available, but all the time. Please remember that. Here, the channel is available for short duration for just the time allotted to him, but entire channel, entire bandwidth is available to him. Because this entire bandwidth is available, he can transmit at higher data rate. And again, comparing, taking the same example, assume that this is 30 megahertz uh, total bandwidth. All 30 megahertz bandwidth is available for one slot duration to the first user. That means he will be able to transmit at 30 Mbps, but only for the duration. Next time slot, second person will get the entire capacity, all 30 Mbps. Similarly, third user will get in third, fourth user will get third, fourth. So like that, during his slot time, the entire capacity available, he will be able to transmit at much higher data rate. Okay, but that means he is getting his time slot in turns. So once all of these things are over, then again first user gets again his turn, next second user, next third user. Like that you can go on allotting in a certain, but for the simplicity, assume that round robin purpose, simplicity purpose. Okay, all of them will getting this entire channel, so that it is at the receiving end again. Each time slot is because they are already allocated to them. During that time, whatever data comes, that is passed on to the first user. Second time slot, second user. Third slot, third user. Fourth time slot, fourth user. Again, fifth one again to first user. Sixth to second user. Like that, and round robin rotation, each one gets his turn. So that again here also, during this time he receives 30 Mbps at 30 Mbps rate, and he will be handed over to him. That's how it generates. Okay, but in case they are generating much higher than what can be carried here, then of course there is a problem. We have to ensure that the combined data rate of all these users, okay, at input should not be more than the capacity of the channel. Then only this scheme works. Okay, the combined data rate of all these users should not exceed this one. Okay, then only it works. Right? TDM is a digital multiplexing technique for combining several low rate channels into one high rate channel. Okay, as you have seen, these are different low rate channels, because all these together is equal to capacity of this one. Okay, so this is a single channel but higher data rate. Now, it's more detailed manner, you can say. First one, say he is generating, assume that data is coming in small characters or packets. Okay, first packet is come, second packet, third packet, he is generating in this fashion. And similarly, B is generating this he is generating. Now, while you are sending it, what you do? First, you can always send first character of A, you can see here, and then first character of B, third character of first character of C. Then second character of A, second character of B, second character of C. Then third character of A, third character of B, third character of C. So like that, this channel is shared by all the people. You can see if you take this as a frame, okay. So that means the frame carrying all input users data. So in that he is getting only 1/3 of the part. Within that his data is sent. So remaining two parts are shared by, again next frame starts. Again next frame again 1/3 he gets. Again third frame again he gets 1/3. Like that, everybody is getting in turns his sometimes slot to transmit his data. So in synchronous, here if you see here, these are perfectly synchronized. when first one is sent, when second one is, third one is sent. That's why we call it a synchronous time division multiplexing. In synchronous time division multiplexing, the data rate of the link is n times faster and the unit duration is n times shorter. Okay, so what is this one? This data rate is n times faster, multiplied by 3 times to any of them, right? But at the same time, duration of this one, when the data rate increases, time this duration of each of them gets, automatically reduced. So it becomes one third. Becomes one third compared to data rate of duration of bit duration of here, bit duration of here. If you compare it, this will be one third of any of these. Then only this TDM will work. Now this is an example. Data rate for each input connection is 3 kilobits, and if at a time, what is this one? 10 kilobits. 1 minute. Duration. Each input slot, each output slot. We have to calculate each time frame. We can answer the question as well. Data rate of each input connection is 1 kbps, right? And this means that bit duration at the input is 1 divided by 1000 seconds, 1 milliseconds. Time duration of input slot is 1 milliseconds. Okay, same bit duration. Now, duration of each of the output slot, it will be one third of it, right? So here it is 1 millisecond, then becomes one third of millisecond. Okay, and each time frame carries 3 outputs. So that means 3 multiplied by one third of it. So it becomes 1 millisecond. So if you assume the same thing here, if it is coming at 1 kbps, here bit duration is 1 millisecond, whereas here bit duration becomes one third millisecond. But the entire frame will be take where 3 bits, one from here, one from here, one from here, taking care. Total together it becomes 1 millisecond. So that's what. Of course, this is another example. Same way we can calculate it. Okay. Now, assume that frames are yeah. So here, instead of characters, here we are taking as a bit here. Let's say 1 bit here, 1 bit here, 1 bit, 1 bit here. So 1 0 1 0 becomes first frame. Next, second bit of each of them becomes second frame. Third bit of each of them, fourth bit of fifth. So like that, every frame is generated in set. So this is another example. You can look at that. Multiplex together. 1 bit. Find a duration of 1 bit before multiplexing, the transmission rate of a link, the duration of a time slot, and the duration of time frame. You can see the example answers here. So time duration of 1 bit before the multiplexing is, because it's 1 kilobit per second, and it's 1 milliseconds. The rate of the link is 4 times the rate of connection. So that means 4 kilobits. Okay. So that's how you can calculate it, and these things need to be. We have seen this one interleaving purpose. Okay, let's see what is interleaving here. So we are sending A1 here, B1 here, C1 here. This is one frame. Next frame becomes second part of A, second part of B, second part of C, and third part of B, third part of A, third part of B, third part of C. Right? These things will be perfectly synchronized. So this one bit from here, one bit of one part here, one part here, one part here, putting into this, we can also call it interleaving. That means one data is not going continuously.